All right, should be about time. All right. Good afternoon, everybody. Welcome back to DSP. Okay. A few announcements. Your midterm has been graded, so please pick it up during the break. And then otherwise, we are going to continue our discussion on filter design. Okay. Today, I'll first try to finish our discussion, our introduction to infinite impulse response, IIR, that kind of filter. And then there's this other kind of filter called FIR, finite impulse response. I will enter that topic today. Okay, so please have a seat. All right, so otherwise, tomorrow we are going to have a discussion session, a follow-up discussion session. So please stay tuned. If you haven't looked at the problems, please take a look. And a bit about the grades. My TA told me that the average, 平均多少分呢？83分。Okay, so the average is pretty high, and many of you get above 90. That's great. That's higher than I expected, but good job, everybody. So just please stay tuned, but and come to Thursday meetings, okay? Because Thursday meetings are important for you in terms of your final grades. Obviously, you know that, right? Whenever you ask a question, there's one extra point. So please, if you really aim high for this, really high in terms of the score, if you want to get the high score, please come to Thursday meetings. It should be pretty obvious now, okay? Any questions so far? All right, so let's take a kind of a preview where we're at last week. So Butterworth IR filter. Butterworth is a kind of filter which has an analog prototype, right? Analog prototype, and we have seen that if you arrange a transfer function in the S domain like that, putting several poles around one circle, and the circle that circle has a radius of omega c. Okay, in the S plane, not the Z plane yet. Okay, not yet Z plane, just S plane. If you place the poles like that, then from there you can show that the magnitude square as a function of frequency turns out to be has a very nice expression, which is monotonically decreasing with the corner frequency exactly placed at that frequency, omega c. Okay, so that's a fairly nice property, and here n denotes the order. Okay, make n bigger, you get a faster transition. Okay, and you can check that. So last week we spent much time on checking why this is the case. This is not that trivial, but hopefully either n could be even, n could be odd. This expression is valid for both cases. Okay, so really. Just we have checked that if you just place a poles like that around the one circle, and you get this very nice monotonically decreasing magnitude response, which is very nice. And then, so we have made sketches of how we have seen how the response varies as n increases. With the same corner frequency, when n increases, you get a narrower transition. The transition becomes narrower. Okay, the gain drops from 1 to 0 more. Faster, more rapidly. So now we've done that sketch, and now the question is, how do we make use of this prototype and transform it so that we have a digital filter? How to go from analog to digital? And the answer is using bilinear transformation. So let's take a look. So we take a look at here. Bilinear transformation is a function from Z to S. We can define S as a function of Z. Define S as a function of Z. So there will be 1 minus Z inverse, 1 plus Z inverse, and there's a parameter 2 divided by TD. Okay. So that's just simply a definition, and where TD, as you will see, can be adjusted. Okay, can be adjusted, and then with this transformation, we can go from analog to digital using this equation. Okay? Let's say H is the prototype. Okay? H is a function of S. So H is in the S domain. Now, whenever you see S, just substitute. Make a substitution. Rewrite S as a function of Z. Is that clear? 重写一遍啊. Whenever you see S, rewrite S as a function of Z. And then the result will become a function of Z. So this composite function 就是结合啊，函数的结合啊。Composite function G, let's call it G. G will be, we argue that G is already a design. It's that simple. Coming from, just start with an analog prototype and then by substituting S as a function of Z, 就是变数变换啊。By doing this substitution, we have a function of Z, and we claim that G of Z, you can just organize the top and bottom. In general, it's going to be our old friend B of Z divided by A of Z. You can write it in that format, B of Z divided by A of Z. And then we know that when you reach that expression, when you have that expression, then it's rather straightforward to find the difference equation corresponding to BZ divided by AZ. Yeah? So, okay, so we call that already a design. So today, our job is to take a closer look. How come we say this is a design? How come we? Because like operation-wise, in terms of just doing the calculation, it's pretty straightforward. In terms of doing the calculation, just follow the steps, find B of Z and A of Z. Calculation could be tedious. 有可能很琐碎, but it's rather straightforward. 琐碎但是还蛮直截了当, okay? So operation-wise, calculation, in terms of calculation, it's not that hard. But I think the key point I want to deliver today is why can we say this is a design? Why? Yeah, it should be pretty surprising, okay? But here is a nice little exercise which we might use from time to time. If S is a function of Z, and bilinear transformation, bi means bidirectional, right? Yeah. So Z can also be expressed as a function of S. Okay, let's maybe work this out. There's an exercise. We can try to say find Z as a function of S. So if S equals to 2 divided by TD, 1 minus Z inverse, 1 plus Z inverse, then TDS divided by 2 is 1 minus Z inverse, 1 plus Z inverse, right? So from there, we can say, let's work this out, okay? TDS multiply, how about we do this? Equals 1 minus Z inverse. And therefore, what's next? So let's move 1 minus TDS divided by 2 to the right. Okay, there's things with this term. And on to the left, we have Z inverse, what? Z inverse times 1 plus TDS divided by 2. So we are almost there. So therefore, Z is 1 plus TDS divided by 2 divided by 1 minus same thing. Okay, so here is just a nice little quick exercise. We can also express Z as a function of S. So in general, bilinear transformation is a mapping from S domain to Z domain. And since the inverse function has been written out, so we have found the inverse transformation. So this is basically a one-to-one mapping. Okay, one-to-one mapping between the S-plane, real S, imaginary S, between S domain and Z domain. Okay, so we're gonna leave everything for now on the board. I will come back to my plot later. Right? Any questions so far? S as a function of z, z as the inverse function can be also derived. Okay, you can also derive the inverse functions. Pretty straightforward. So far, so good? Huh? Okay, so here I want to just go a few steps further using the third order Butterworth as an example. Okay, so the third order Butterworth as an example, if we just really do this substitution, h of s is known, right? H of s, but whenever you see an s, you see here is where s appears. Okay, here's one location where you see s. Replace it with s of z. Okay, and here, that's the only place, right here in this formula. But when we 把它爆开, when we expand the three terms, now you have 1, 2, and 3. Okay, this is a second order polynomial, and this is just simply s plus its first. That's where the one pole is located, and now you have this. So seriously, this is what you should do. There are three terms. Multiplication is a product of three terms. So at the bottom right here, whenever we see s, replace it with s of z. That's what we mean. Is that clear? Replace it with s of z, and that's why I say it could be pretty tedious. Right? It could be pretty tedious because now you have square, right? So things are going to look dirty, but nonetheless, it's straightforward. Okay? It's not hard. It's just dirty. Okay, so you can do that, but that's not the end. Okay, because in the end we want this expression to be in terms of b of z divided by a of z, where b and a are both polynomials, right? But do we have polynomials here? Not yet, right? This is not a polynomial of the inverse. This is not. So we need to move some terms around so the final expression becomes b of z divided by a of z. Because this is not a polynomial yet, okay? So we are not happy yet. So what should we do? We should try to make the bottom a polynomial by multiplying this bottom part with 1 plus z inverse to the cube to the third power. Okay? So let's multiply the top and bottom both with 1 plus z inverse parenthesis 刮弧 to the third power 三次方. So hopefully by inspection, can we agree that after doing that, after we multiply top and bottom with 1 plus z inverse, let me write it down. Just multiply now with that omega c third power over large big thing. Here is whenever I see an s, okay? S plus omega c. Actually, we've done that last Thursday, right? That's last Thursday's, that's in your homework, okay, which is due tomorrow. So whenever we see s squared plus omega c s plus omega c squared, But every s has but s equals to 2td 1 minus 1 plus, okay? So the problem is this term right here, That's giving us some trouble. This is where the trouble is, okay? So to make the final expression equal to bz, to organize the final expression into this format, I suggest that we multiply the top and bottom, just 同乘以, we multiply top and bottom with 1 plus z inverse to the third power, okay? So that here is a 1 plus z inverse. Here is a 1 plus z inverse, and here's also a 1 plus z inverse. Okay, so multiply. Just do it carefully. Okay, multiply top and bottom with 1 plus z inverse to the third power to remove, so that now the top and bottom both become polynomials. Can we do that? So that the top and bottom will both become polynomials. The bottom might look like, so this, after doing that, then b of z seems to be just omega cutoff frequency third power 1 plus the inverse to the third power. We get this, okay? But how about A of z? A of z, I will not find the final expression because your computer, MATLAB, can do it for you. Okay? MATLAB does it for you, but here the kind of derivation would be something like there's 2 over TD, 1 plus z inverse, and then plus omega c. There's also 1 plus, no. Yes, no. This is minus, sorry. That's minus, okay? You know what I mean. So we use one, so here we have changes to like that. That's the first term, okay? Let me find another color. And so we move this 1 plus z inverse to here, okay? So that's using one of the 3 chances. Because where are the two other chances? 有3次机会了. So the first chance can be used right here. And then here we should just assign 1 plus z inverse, multiply with that. And here under this second term, we will multiply this second term with 1 plus the inverse to the square. Okay? So if we do that, then this is gone, and this is also gone, but now we have one extra 1 plus z inverse, and this has 1 plus z inverse square. So now, do we have a polynomial? Do we have a polynomial? Yeah. Okay. Now, A of z is this times something square plus omega c something 1 plus z inverse plus omega c square 1 plus z. So that's A of z. We happy? Huh? Yes or no? So I said this is pretty tedious. That's why we need MATLAB or Python or any library, okay? But theoretically, you can just complete this calculation. We're not happy yet, actually. Yeah. Why not? Okay. Anybody tell me that this is not yet A of z? And this is actually not yet B of z. Something is wrong. One tiny little bit. The inverse is, or reverse is everywhere. This is polynomial for sure. This is polynomial, this is also polynomial, but the leading coefficient of A of z, 首次的系数啊，常数项数 the constant coefficient of is not yet 1. So if you find the corresponding difference equation, that's okay. Please normalize. Then still, should I say this is A? Not yet. A. This is can be say this is A. I don't know. I'm running A almost. A 几乎啊 ，A 几乎 ，A sub 几乎啊 ，B sub 几乎啊。But then we still need to normalize so that A becomes, let's say, A of z. The final A of z should be A 几乎啊 ，A 几乎 of z divided by some kind of constant, okay? So that A of z is equal to 1 plus something z inverse plus something. It's a third power, so we have 4 terms. Something. Now, usually we like the first coefficient to be 1. Okay? So that the corresponding difference equation is in the right format. Okay? So there are tiny little details, okay, just for your reference. For us to appreciate this. Could be tedious, but it's nonetheless not hard. It's not that hard. Okay? Any questions so far? Yeah, we can do it. Follow the steps, substitution, organization, and renormalize so that A of z has a leading coefficient of 1. Then everything should be fine. Okay? Yeah. Okay, so you can design a third order, but still, this is just about calculation. But next, we want to just study a few properties of a bilinear transformation so that we can be convinced that this really gives us a good design. Okay, this difference equation really has basically the same frequency response as our analog prototype. Okay, why can we call this a design? Okay, well, why can we call it a design? So there are a few properties that we can be aware of. The first property is that since bilinear transformation is a mapping between S and Z, so the first most important property to know is that the imaginary axis in the S-plane will be mapped to the unit circle of Z-plane. Okay, so let me just draw it. So let's say, imagine that you are going like bottom to top, going in this direction along the imaginary axis in the S domain. Okay, imagine that going up. You walk along like that. Then transforming to the Z domain, the path, the contour becomes a circle. Actually, the unit circle. We have, I believe, have we shown that? Yeah, it's also part of your, is it part of your homework? I forgot, but it's rather easy to show. It's rather pretty easy to show. Okay, it's rather pretty easy to show. You just need to show that. But that's a result. Okay, it's going, and I mean the imaginary axis is mapped to the unit circle. Okay, yeah. That's property one. Okay. So let me let me just introduce all the properties before we dig into details. Okay. So that's the first property I claim to you. Yeah, that the bilinear transformation is a mapping between S and Z, and in particular, the imaginary axis is mapped to the unit circle. So therefore, this implies a relation between big omega and small omega. You can make a derivation. Yeah, you can make this derivation. I believe we've done that last Thursday, okay, in both sessions. Chinese or English session, we've seen this, right? Yeah. There's a relation between big and small omega, where big omega really is radian per second, small omega really is your DSP, okay? Is the omega in DTFT. It's really the omega in DTFT. Okay, there is this relation. Okay, so quickly, I think we should just show it to make sure that we understand what's going on. Okay. So how do we show it? Let's say which direction should it go? I think it might be easier this direction, okay? So let's keep this. Let's say from here, that's Z as a function of S, okay? So if S is J omega, where does it go? Where is this mapped to the Z to the Z plane, right? So we just substitute S with J omega in right here. Then here we get Z equals to 1 plus J TD divided by 2 big omega divided by 1 minus J TD divided by 2 omega. And it's rather easy to show that Z. Now, therefore, first of all, Z has a length of 1. So just by this very simple argument, we have already shown that the imaginary axis is mapped to the unit circle. Right? Because whenever if S is on the imaginary axis, then Z is on the unit circle. Yeah. That's what we are showing. Is that clear? If S is on the imaginary axis and you write it as S equal to j omega, then Z absolute value is 1. That implies Z is on the unit, somewhere on the unit circle. So then our next job is to find out exactly where. We say somewhere. From now, it's already pretty obvious that it will be on the unit circle because that absolute value is 1, right? But now technically, where exactly on the unit circle? That's our question. That becomes our question, right? Yeah? So if you're with me, next, how do we find out exactly where on the unit circle is S mapped to? Right? To where? To which point is S mapped? Okay. So now, if Z is on the unit circle, we can say Z equals to what? Equals to e to the j small omega, right? Parameterize, we can parameterize the unit circle. Let's say we are interested in find out this angle, okay? If given a point, any point j omega right here, where exactly on the unit circle, what's the angle? What's this angle? If S is j omega, okay? What is this angle? What is this angle? Okay? And from here is probably the way I like to write it is that now this angle, since right here we have a division, right? We're dividing one complex number by another complex number. Therefore, the result, the angle of the result should be the difference, should subtract. You should subtract the angle of this term from the angle of that term. Take the difference, because we're dividing complex numbers. So the angle goes through a subtraction, okay? So what I mean is that this angle should be the first angle on top. This complex number has an angle minus the angle of actually its complex conjugate. Okay. So therefore, what is this angle? The angle right here is exactly arctangent of the imaginary part divided by the real part, which is 1. And similarly, the angle here is just minus arctangent TD omega divided by 2. So that's why. Just imagine that we have two complex numbers, okay? And we know that the angle of one complex number is arctangent. It's quite kind of nice to be reminded that the angle of any complex number is arctangent of imaginary part divided by the real part. So now, finally, you have a factor of 2. 2 arctangent TD omega divided by 2 equals to what? Oh, equals to omega. Yeah. Omega being, where is this angle, okay? So since small omega, we can now is a function of big omega. And the inverse function exactly is that, okay? Then big omega, small omega, okay? We have this very nice relation, okay? And which we'll come back, okay? Well, this is important, okay? Now we have a one-to-one mapping, basically, between small and big omega. All right. So far, so good. So that's a derivation where I think our presenters last Thursday also showed the same kind of thinking process. Okay, same thinking process. Because of bilinear transformation, we have checked that the imaginary axis in the z domain is mapped to the unit circle. and there's a relation between small omega and big omega. There's a one-to-one mapping. The one-to-one mapping between the entire imaginary axis and the unit circle. Okay? Now, should not be surprising, right? Does anybody find this surprising? Historically, it could be surprising, okay? Because now it's a very good example of mapping an infinitely long line to the circumference, 到圆周. But the circumference has a finite length, right? The arc length is 2 pi r, 2 pi. So we are mapping an infinitely long line to the circumference 圆周 of the unit circle, which has a length of 2 pi. But that's a natural property of the tangent, right? Tangent does that. Tangent does that, okay? Or the other way around, tangent maps the finite interval of 2 pi to entire, the set of the entire set of real numbers, okay? Infinite line and finite interval, okay? You can find a one-to-one mapping like that. You can construct a one-to-one mapping between a finite interval and an infinitely long line, okay? It's doable. Tangent does that exactly, okay? So that's a very useful relation, and yeah, this is the first property. And going from the first property to the second property, okay? I want to invite you to think about, let me read it, okay? Turns out that the bilinear transformation is also one-to-one mapping between the left half plane in S and the inside of the unit circle. The left half, right here, the entire left half plane is mapped to the inside of the unit circle, okay? And you can also show that. Okay? But intuitively, this is a kind of a nice property about orientation of a contour. Okay? I say orientation of contour. 那个轨迹啊，它可能有一个方向性啊。Orientation. How do we explain? So we know that S is a function of Z, or Z is a function. Yeah, let's say Z is a function of S. Here, okay? Z as a function of S. Going from S to Z domain, okay? So the principle is that this is a property of complex function with a complex variable, okay? 复变的一个 basic property, which says that if you have a kind of closed contour and the orientation is counterclockwise, okay? And you take it from S to Z. In general, if your mapping is so-called analytic function, 解析函数 if f of s, if z equals to f of s is analytic, in the sense of Cauchy-Riemann symmetry, okay? In the sense that its real part and imaginary part obeys the Cauchy-Riemann relation, 柯西黎曼的关系 analytic function, so it becomes differentiable 这类的 If you have a differentiable function, and which is this differentiable? Yeah, almost everywhere except at this pole location, okay? But everywhere else, z is a differentiable function with respect to s. 对 s 是可微分的。Under the meaning of here, really everything is complex numbers. So if z is analytic, then when you start in the S domain, going around the contour in this orientation, let's say counterclockwise, then it turns out that in the z domain it should be also counterclockwise. The z domain, the shape can change. Your shape can even be ugly, okay? But still, it's counterclockwise. And furthermore, what stays on the left? What is on the left stays on the left. Left-hand side is still the left-hand side. Inside is still inside. Outside is still outside. if I understand correctly, okay, inside should still be mapped to the inside, okay? Outside to the outside. Okay, so, all right, good. So I want to invite you, okay, to think, but now here, this is not a closed contour, right? As imaginary line is an infinitely long line, right? But let's apply this property. What's on the left-hand side should still be in the left-hand side after the transformation, okay? So left-hand side of the imaginary axis obviously should be the left half plane, right? But how about the left-hand side of this contour? If you go counterclockwise, what's the left-hand side? Is the left-hand side inside or outside? If you go around the circle like that, your left-hand side is, imagine you're going, right? You're an ant, or a bug, or snail, or whatever, or a snake, or a lizard, okay? Going around, what's your left-hand side? Left-hand side is inside, right? Left-hand side is mapped to left-hand side, okay? That's a pretty basic property about functions of a complex variable, okay? And this has a nice implication, okay? This has a nice implication, which is point number 4. But let me explain. There's a third property, okay? Now, the next property is that, in general, this equation 1, I say, is analytic, okay? And an analytic mapping, an analytic function defined on the z-plane, has a property of being conformal, okay? This mapping will be a conformal mapping. Conformal mapping, have you learned that? Have you learned the concept conformal mapping? Have you heard of it? Yes? No? Have you heard of conformal mapping? Yeah. Conformal mapping in Chinese is 保角变换. It means that somehow the angle is preserved. Literally, 保角嘛，保持角度, the angle is preserved. In what sense? In the sense that, imagine if you have two vectors. Yeah. Imagine again that we are on the, let's say, if we are on the S-plane to begin with, either way. So let's say this is the S-plane. And at any given point, any random point on the S-plane, okay, imagine that you can go in an arbitrary direction, start moving with a infinitesimal step, 一小步, 跨出一小步. Just going along a certain direction with an infinitesimal, really, really small, let's say S and ds. And this is ds1, okay? There's one possibility you can start at this location S and go one tiny small step toward a certain arbitrary direction, okay? And you can also go toward another arbitrary, now I'm drawing a really big, but imagine this is a very small step, okay? Just for the sake of drawing, I make this arrow a long arrow. But two infinitesimal directions, two very small steps along S1 direction or S2 direction, and there's an angle. Let's say the angle is difference is phi, okay? Yeah. That clear? Yeah. So now we have an analytic mapping, which is z equals to 1 plus td divided by 2 divided by s, 1 minus td divided by 2 multiplied by s, okay? This is an analytic function defined on S, okay? So we said that this transformation now going to the z domain should preserve the angle phi. So that means now going to the z domain, first of all, going to the z domain as will land somewhere in the Z domain. Okay, let's say S now is located right here. Doesn't really matter. Z of S. Okay. But now, how does this small move? How about this small move? Okay. So by moving from S to S plus ds1, so now the corresponding move might be in any direction, okay? So z of S plus ds1, okay? Z as a function. Here, z is a function, okay? Z as a function. Now this point also move infinitesimally, one very small step toward a certain direction, okay? And then how about S2? Now z can also move toward a certain direction. This is z of S plus infinitesimal ds2. But now, in general, these two directions are not going to be same as these two directions, okay? But what remains the same is the angle in between the two directions. That's what we mean conformal, okay? This angle phi is preserved after the transformation, okay? If a transformation has this property, then we say that the mapping is conformal. We have a conformal mapping, 包角变换. And this is something deeply rooted in the fact, this is a consequence of the fact that z is differentiable. Z as a function of S is differentiable except at its singularity. 它可能有基点啊，起点 singularity, except at one singularity. Otherwise, everywhere else, Z is a differentiable function of S. Therefore, it preserves the angle like that. It is a conformal mapping. Okay? So why do I want to mention this? In tomorrow, any questions so far? So far so good. Conformal mapping. Tomorrow, I invite you to think about, all right, now, the imaginary axis is mapped to the unit circle, and the left-hand side is mapped to the left-hand side, which is inside. But how about, turns out that all the lines, all the straight lines, such as all the lines parallel to the imaginary axis, to the left or to the right, all the straight lines turned out will be mapped to a circle. And left-hand side mapped to the left-hand side, okay? So all these straight lines are going to be mapped to smaller circles inside the unit circle. Okay, so in tomorrow's discussion, I asked you to find out what exactly they are, okay? You can find out the expression. Straight lines are mapped to circles. And also horizontal straight lines are also mapped to circles. So we have two families of circles, okay? And the angle should be preserved. Okay, so here, all the vertical lines and horizontal lines are crossing each other at right angle, 直角, 对不对? Right angle. But here, I suggest you can find out that all the circles corresponding to the vertical lines and the other family of circles corresponding to the horizontal lines, they're also perpendicular. 垂直的, You will find two families of circles which are perpendicular everywhere they meet. In Chinese 是你会发现有两组圆到处都互相正交 kind of a nice property. I invite you to think deeper, dig deeper in this. It's a very nice example of what it means for mapping to be conformal, preserving the angle. Right angles right here in one domain, right angles in the other domain. Okay? 对人生没有帮助 but it's kind of nice to know. Right? So tomorrow I invite you to, when we come back, I invite you to dig deeper. Conformal mapping, so yeah, left-hand side to the inside, imaginary axis to the unit circle, okay? So let's finish this slide before we take a break. Okay, yeah. So 1, 2, 3. How about the fourth property? The fourth property is a property about stability. Okay, so let me read it. Now imagine that since the left-hand side is mapped to the inside, okay? So remember that when we design the prototype in the S domain, we draw a big circle with radius omega c, right? And we are placing poles right here by cutting pizza, kind of, yeah. Cutting pizza. Okay, yeah. So we place the poles on the left half plane in S domain. We didn't emphasize this, but there's a reason why we put the poles to the left-hand side. We place all the poles to the left of the imaginary axis. So as, what's the purpose? The purpose is so that the analog prototype corresponds to a stable system. If you apply the inverse Laplace transform, the impulse response converges to 0 when t goes to infinity. Okay, we begin with a stable design, stable analog design. This system is not going to oscillate or doing anything funny like that. Okay, you begin with all the poles to the left of the imaginary axis so as to ensure stability. That's in the analog domain, in the S domain, analog domain. But when we go to discrete time, now it's good. It's kind of comforting. 让我觉得受到安慰啊. It's really nice that all the poles here are going to map where? They're going to be mapped to the inside of the unit circle. Okay, so now from S to Z, this is Z plane. Now these poles, wherever they are going to be in the inside of the unit circle, might be something like that. We have equally many poles now in the Z domain, but all of them are guaranteed to be inside the unit circle. And isn't that great? It is great, right? Make the response great again, right? Because if all the poles are still inside the unit circle in the Z domain, we know that this system, this corresponds to a stable and causal system. Yeah, none of the poles will go outside. Okay, so that's pretty nice. Stability is preserved under bilinear transformation. Let me repeat that. Stability is preserved after bilinear transformation because all the poles are going to go inside the unit circle. Okay, to ensure that now our design, which I just erased, 我们刚刚擦掉了, that design will be a stable system because all the poles are now inside the unit circle in the Z plane, on the Z plane. Okay? Stability is preserved. Stability is preserved. And that's pretty important. Every time we have a singularity in the Z plane, then after transformation, the singularity goes there, which is inside the unit circle, given that S is to the left-hand side of the imaginary axis. Okay? Therefore, stability is preserved after bilinear transformation. Very strong property, strong and important property, useful. And then finally, we have shown that. Okay, we have shown that because of that kind of tedious work, B of Z will contain a factor of 1 plus Z inverse to the nth power on top, B of Z. Okay, B of Z on top in the numerator. Okay, in the numerator part has a factor of 1 plus Z inverse to the nth power. Or in other words, we have the case of a multiple root. Okay, we have a place of we have the case of a multiple root of B of Z. Okay, B of Z basically will be exactly 1 plus Z inverse to the nth power. Okay, yeah. So let's take a break. Okay, so when we come back, then we look further what this implies. Okay, about this relation between big omega and small omega. 啊，对，那可以来领考卷啊。用发的也许，你这样子可能会用发的，用一个叫对啊，念名字吧。你不念错就再确认了。那2位一起发了，2位助教一起发啊，一份一发啊。有没有洪亮一点好吗？啊，洪亮一点。呀。 喂，那个大家领完考卷哈，so please keep your own answer sheet and I do not suggest picking other people's. Yeah. Please do not pick other. Please refrain from picking other people's answer sheets. OK， 自己拿自己就好，好吗？呀，不要帮同学代拿。OK，so we do not recommend picking up the answer sheet for your friends. OK, ask them to come to the TA. OK, so I'll ask the TA to collect whatever that's left on the table. We'll collect them and bring to our lab. So 一定要亲领啊，亲自领啊。Please only receive your personal answer sheet. Okay, Okay, so can we just slowly all return to our seats? Let's all return to our seat. And let me, so I think I can tell you, the average is 83.7. 平均分数这是83.7啊。The average is 83.7. Okay, and if you fall behind, please don't feel too bad because the average is pretty high. Okay, so if you're doing 70 something, you 及格的话 is not bad. Okay, not bad. So I want to share with you a personal story. Okay, 我就讲中文好，我就讲一个，因为有时候我觉得大家会因为某个科目考好，就对某个就觉得说我比较在行啊，某个科目考不好，就说我跟这个没有缘分啊。Don't say that too early. Okay, so it happened to me. When I was at Stanford, so we all had a PhD qualifying exam. So I aimed for PhD when I arrived at Stanford. And the quality in the 资格考啊，博士班资格考啊 PhD qualifying exam. So the rules were we all need to each of us meet with 10 different professors. 每个同学要去跟，你可以选志愿啊。You need to talk to 10 different professors and they'll test you. They'll give you a few questions and you need to answer them in 10 minutes. So 10 meetings of 10 minutes is very stressful. 非常有压力啊，你一 stuck 就觉得完蛋了啊。So luckily I passed the first time. But there's one professor who gave me 3 out of 10. 就是满分10分，有某个 professor I still remember his name. His name is Fabian Peace. Okay, I can say that. So you remember like tough professor for a long time, Fabian Peace. I still remember his name. Fabian Peace, whose specialty is E-beam lithography. Lithography 半导体制程啊，physicist. Yeah. Professor Fabian Peace gave me only 3 out of 10. After meeting with him, he gave me a hard time. Luckily, I still passed. So I tried to avoid taking his class ever. But then, quite a few years later, 6 years later, it took me 7 years to finish my PhD. Okay, finally, when I was about to arrange for my oral defense, 口试要安排嘛 right? And at Stanford, the department required us to find a professor that is out of your field, absolutely out of your field. Okay, and my field is signal processing, right? So semiconductor manufacturing is absolutely out of my field. So I had a hard time we need to find that one professor to chair our oral defense. 那个主席必须是 out of field. 你不可以说就找老师熟悉的老师啊，不行。You need to find somebody out of your field to chair your oral defense. 这样了解吗？啊。And Stanford professor were all super busy. So I sent email. I even asked 我的硕士班导师他不理我。Yeah. So I had a hard time. I sent emails. I sent invitation to I think almost 20 professors, but they all say that they either didn't reply or they reply like immediately that they are too busy. They had no time. That's how busy they are. So I couldn't find anybody, so I seek help at the department office. 我去系办问，是不可系办的姐姐可以帮我一下，推荐有哪些老师可能可以找。他就看一下，哦，你领域是讯号处理。How about Professor Fabian Peace 啊？然后我就心里面就冒冷汗，我就是 He's probably the last person I wanted to find. But then I sent him an email, yeah, and immediately his secretary replied, Professor Peace does not have time. But I sent a very interesting email, okay? But so later at night, Professor Fabian Peace replied. 他就是等于否决他秘书已经回信给我了，就说老师没时间。不过后来稍晚他回信给我，他说他有时间了，因为他看了我的信觉得很有趣。What did I write? I said, President Fabian Peace, you hold a special place in my heart because you gave me 3 out of 10 when I was doing my PhD qualified exam. I remember you for that. So you hold 你在我心中是有个很奇特的地位在那边。他就说他任教20年，从来没有看过有人这样写。通常大家写给老师，因为我都拿10分，我拿 A 加，所以我希望 Can I have the honor to invite you？ 一般人都是用很客气，觉得都是 honor， 但是我是拿我最烂的 performance 来跟他做 sharing。结果他就说这太奇特，他一定要 host 我，所以他就回信说他可以。后来我的口试他帮我大忙啊，帮我非常大的忙。So never say never, okay? Even before I did my oral defense, he invited me to give a 20-minute version, a condensed version of my presentation to his group. And everybody's out of my field, so I get a chance to practice, to rehearse my talk. It's really helped me a lot. I still now still remember him. Okay, so 如果考坏了啊，没关系，过几年想要找我帮忙，就是说老师，我当初期中考56分。And you hold a special place in my mind, so I will help you. 好吗？So don't be feel too bad. Okay, never say never. Okay, so enough of my personal sharing. Fabian Peace, nice guy, decent scholar. Okay, let's come back to big omega and small omega. Okay, so now we have a relation between the small and the big omega. Okay, and one of you actually. That's a very good question. So in the beginning of this semester, right, I was talking about there's a simpler relation between big and small omega. Okay, what is that? That is when we talk about sampling, right? We talk about discretizing our time axis. Okay, so we go from a continuous time function to let's say when we do A to D conversion, we receive an input which is continuous in time, and then it produces an output with a sampling period, right? And the output is x of n equals to x continuous time evaluated at n times big T, right? So if we do that, then now we go to a frequency domain. There is a simple relation between big and small omega. That's in this context. In that context, what's the relation? Anybody remember what's the relation between big and small omega in this context? The relation goes big omega equals to small omega divided by t, right? That's when we talk about sampling a signal, okay? But now we have a different relation because the context is different. Now we are designing a filter, okay, by borrowing an analog prototype. So we are not talking about sampling. We're not talking about sampling, so it's not surprising that we have a different relation. It's just still using the same variables, the same notation, but now the context is different. Okay? So let's be clear that we know the difference we have 2 different contexts. Okay? Filter design versus sampling a signal. Okay? This is about designing a system, this is about sampling a signal. Okay? System versus signal, so 2 different contexts. Two different contexts. 情境不一样，应用情境不一样. So let me clarify that. But now coming back to focus on this equation right here, big omega as a function of small omega. Now we have, and this relation explains why the relation between analog prototype and its discrete time design. So really, long story short, it's about compressing the frequency axis. Let me repeat, compress, 压缩. It's about compressing the frequency axis. In what sense? So now, the analog prototype, in the analog world, the frequency omega can go from DC, from 0 to infinity. So that's the entire frequency axis from 0 to infinity. But now, by using arctangent, the corresponding small omega. So let me erase this discussion over here. By using arctangent basically compresses the entire real line to a finite interval, right? So here we have a situation that small omega is 2 times arctangent of TD divided by 2 omega, big omega, right? And arctangent basically does the compression job. It maps the entire real line to somewhere in between plus pi and minus pi, because we have a factor 2 here. Right? The arctangent is from pi over 2 to minus pi over 2. With a factor of 2, now this is exactly what's happening. The entire frequency axis is now mapped to the finite interval between minus pi and pi, and the slope here depends on this parameter TD, okay, which is not that important. So with this idea, so now that we understand it's a compression of the frequency axis, now we can see what will happen as far as the frequency magnitude response is concerned. Okay, so now we say that h of s of z is our design system. Therefore, the frequency response now, as a function of small omega, is a composite function of h of omega of omega. H of big omega of small omega. Okay, so what does that mean? So that means that at every frequency, let's say this frequency, corner frequency, oh, by the way, notation is still a bit different. Here, the h here is my g, okay? And the hc here is my h. Sorry for the confusion, okay? This is a direct copy from the textbook. Okay? 把它写下来好, yeah. So here, on this slide, or let's just simply draw it. We can take it slowly, no problem. So now, if you want to understand what is g of ej omega at any omega right here, okay? So in this plot, we have the relation of tangent. Now this is pi, and tangent goes like that, okay? Asymptotically approaching infinity, okay? At exactly pi. Because big omega is what? Is this factor tangent of small omega divided by 2, okay? So that's the mapping, the compression. Okay, so now if you want to understand for any omega, what will be the frequency response? You can just go, first of all, just find out omega, and this is going to be, here is going to be big omega of small omega, okay, along this axis. So that's why here on the textbook we have this drawing. Now if we just rotate the frequency response plot by 90 degree right here, just do a 90-degree rotation. 90-degree rotation 转过来嘛啊。Turn it 90 degrees, then here we have the magnitude response, which is our prototype, h of j big omega, as a function of omega. Okay, and what's our prototype? If our prototype is Butterworth, if our prototype is Butterworth, then let's say the Butterworth has a corner frequency right here, and it's almost flat, and then it reduced to 1 over 2, 1 over square root of 2, and it drops like that, right? So that becomes our prototype. And if you just plot it by turning it 90 degrees to counterclockwise, then to evaluate the resulting system, the resulting frequency response now as a function of small omega, just first choose any random omega right here and find out big omega, the corresponding big omega, and then the big omega right here goes here, right? And then what is this? This is a gain. Is that clear? So for every so it's a DC, go to DC, and the gain is 1. Okay? Corner frequency, and then it goes both ways, actually. Corner frequency, no, this big omega C. Corner frequency right here, corner frequency right here. So you can go freely between big omega and small omega. Okay? So corner frequency right here, small omega C. We know that right here the gain should become 1 divided by square root of 2, and so on. So now, still, let's take a plot of a few more points. Okay, now yet another frequency, small omega going up, big omega right here. So the gain is that much. Okay, the gain is somewhere like here, and so on. So let's move further to the right. How about this frequency? This frequency goes here to top. That frequency goes here. Oh, the gain is very small. So that's a way. So you can just keep adding more and more points, and then turns out so you get this frequency response, which will also be monotonically decreasing if your prototype is Butterworth. Okay. So in this sense, by just keep plotting more and more points, you'll figure out that indeed you begin with an analog prototype and you end up with a digital filter design. And the general shape will be the same. The only difference is a compression of the frequency axis. Okay? Now the frequency axis originally is from DC to infinity, but now we compress it to the finite interval between 0 and pi, which is exactly what a frequency response ought to be defined over the region of 0 frequency DC and pi, the Nyquist rate. Huh? So is this good? So I want to share with you this is why bilinear transformation gives us a design of a digital filter. Okay? Design of a digital filter. Monotonically decreasing here in one originally, monotonically decreasing after the design. Okay? This nice property is preserved. Nice property is preserved. Yeah. Any question regarding this slide? Yeah. Please make sure that we understand what's going on right here. Okay, it's going in between small omega and big omega using this relation, this tangent relation, and you'll be able to find out the frequency response given its prototype. Okay, given its prototype. One-to-one mapping. Okay. Okay, so with that, I would like to provide you some extended reading materials. Okay, some extended reading materials. So I didn't know it, but I did my homework. So the Butterworth filter historically was constructed really early. Butterworth, according to Wikipedia, okay, Butterworth was a British engineer and physicist, Stephen Butterworth, okay? So he was interested in designing an analog circuit which has the maximally flat frequency response, but yet providing a low pass characteristics, okay? So he figured out that if we just put one resistor, capacitor, and 2 inductors like that, and by carefully setting the parameters, the resistor has, if the resistor is 1 ohm, and the two inductances are a few, like 3.5 or 1.5 Henry, Henry, okay, right, Henry, H is Henry, right? And if the capacitor is 4/3 farad, then you can show that the transfer function between the output and input, that transfer function turns out to be that of a third-order Butterworth, okay? To be third-order Butterworth. So historically, it's about circuit design. And you can generalize. So if you're interested, there are some further readings you can find from Wikipedia. And my next comment is, this is just optional, okay? Just reading materials also in the appendix of our textbook. So it turns out that we have a few different designs, okay? In one design, we can allow the passband to have ripples while the response decreases monotonically after the corner frequency, okay? There exists such kind of analog prototype, and the name is Chebyshev filter. Okay? And in Chebyshev filter, the magnitude response has this also pretty nice expression, monotonically decreasing after when omega is greater than omega, the corner frequency. Okay? So here Vn is the nth order Chebyshev polynomial. It's a polynomial. So that's kind of a generalization from Butterworth. Generalization from Butterworth. Okay, only this term is more complicated. So as a matter of fact, now the passband can have ripples, whereas the stopband has a nice monotonically decreasing magnitude response. Chebyshev filter using Chebyshev polynomial. And a bit more. Further than that, there's even a thing called elliptic filter. Elliptic, the 椭圆. And now on the right, both the passband and the stopband, now both of them can have ripples. Okay? So in general, so you may ask, why do we want to allow ripples there? Why do we want to allow ripples there? Ripples are not good, right? Being maximally flat is wonderful. Why do we want to consider having ripples? So that may be a question to ask, right? That may be a question. Why do we need to consider allow ripples? Is there any advantage, right? But these are like extended reading materials that you can find in the textbook. So in case you're interested, go ahead and read it, where you'll find that elliptic filter. Here we have an expression right there. U is a Jacobian elliptic function. Okay? And I have no idea what that is. I tried to learn it, but I searched the Wikipedia. It's very complex. I've never encountered it in my career. So, has anybody encountered elliptic function in your career? You don't have a career yet. Maybe. So I had no idea, frankly, what a Jacobian elliptic function is, but extended materials can be found in the textbook. And with that, let's end our discussion for this lecture. Right. So let's take a short break. I'm going to switch to my next presentation. Take a 2 minutes break. 其实我真的觉得我蛮可惜，我那个大学时候大三时候的那个电子学没有拿到90分啊，从此我就觉得我跟电子学无缘了，所以也没有去修 VSI， 也没有修 Analog， 我觉得很可惜啊。我现在想起来觉得蛮可惜啊。Don't be like me, okay? Be courageous, stay curious 啊。Stay curious and stay， 你要常常给自己打气啊！要常常你们每个人都要学会给自己打气啊！真的啊 ，Life will be fine， 对，Life will be fine。好 ，any 还有呀 ，OK， so。再1分钟啊！那个另外一件事情叫 I want to communicate. So for Thursday music, so far, I found that a lot of you like Japanese or Korean songs, which are okay, but 有点大家选的音乐音量偏比较大啊。So tomorrow I'll ask the TA to play softer 音量要降低，不然的话，我觉得有时候。I was hoping that the music will help us focus. Okay, so please consider the kind of music that help you focus. Okay, and I preserve my own right to reduce the volume. 如果我觉得有点太嘈杂，我可能会请那个助教降低音量。I encourage you to find some all different kind of music. There's no limit. Okay, you don't need to confine yourself to Korean or Japanese songs. Yeah. All right. So now with that, let's go for this next lecture. Okay, lecture 8. Now we are at FIR. FIR, finite impulse response filter design, and today in this lecture. We'll focus on the window method. There's another method, okay, but today we focus on the window method. Outline, so kind of the most basic idea is to keep in mind that windowing refers to multiplying our ideal filter response with a window function. It's a multiplication in the time domain. So that's probably a take-home message. You are going to do what we are going to do is to multiply something with a window. Multiplication in the time domain. And this action can be also called windowing. So now window is a verb, okay? To window your signal, okay? Window is a verb. Windowing in time corresponds to convolution in frequency, okay? And this could be confusing. This could be confusing, okay? I want to make sure we notice this. Why do I say this could be confusing? Because what is a filter? Filter is convolution in which domain? In the time domain, right? So in order to design a filter which we use for convolution in the time domain, we apply multiplication in the time domain in our design process. And this design process results in convolution in the frequency domain, which is exactly the opposite. So I say this might be confusing. This might be confusing. Please still keep in mind that the result of our design is still an impulse response, which is supposed to convolve our input signal in the time domain. But it's just like when we design the filter, we apply multiplication in the time domain during our design. Okay? And the kind of consequence is convolution in frequency. This we do know. Okay? We know this. Because multiplication in time indeed results in convolution in the frequency domain. That's for sure. But the context should 你要稍微想清楚一点啊 could be confusing. And then outline number 2, in the design process, we will touch on this Gibbs phenomenon. Okay? We'll encounter Gibbs phenomenon. Okay? Exactly how. we'll see that, okay? In the design process, we'll encounter Gibbs phenomenon. And then, unfortunately, Gibbs phenomenon gives us some limitation, okay? So we need to consider how to, Gibbs phenomenon causes a ripple that cannot be suppressed, okay? So in order to suppress the Gibbs phenomenon, suppressing the ripples, we need to carefully choose a window that does the job, okay? And this part, I'm sorry that I apologize that the handout is still under construction, but here is the outline already. First, we talk about the basic concept. Then we talk about a problem that will be encountered, which is Gibbs phenomenon. And then after that, we introduce how to choose windows in order to suppress ripples. Okay. So first thing first. You have seen that this function, the sinc function in time, in discrete time, this is the impulse response for an ideal low-pass filter, which has omega c as its cutoff frequency. Okay, we have seen that quite many times. We've already seen that many times. But as I introduced earlier in this semester, this ideal low-pass filter cannot be implemented. Why? First of all, this G of n is not causal, right? It's not causal because it has a negative time part. It's symmetric around time 0. So G of n is symmetric. It's going to be symmetric around time 0 with this kind of envelope, the envelope is that of a sinc function. And otherwise, if we have a high sampling rate, we have a G of n. Do I call it G? Yeah, G of n. It's going to be an evenly symmetric function around time 0. And it also extends to the right and to the left infinitely. Okay? It's infinitely long, non-causal, and infinitely long to the right also. So it cannot be implemented, at least to the best of my knowledge. You will need infinite memory to store the entire waveform. So it cannot be implemented. Okay? So therefore, we suggest that it makes sense to truncate G of n. If this is our ideal filter, we know that it's ideal in the sense that after Fourier transform, the frequency response is low pass, okay, with a cutoff frequency at small omega c. It's an ideal that the gain is 1 in the pass band and 0 in the stop band, and this sharp transition. The pass band and stop band just 无缝接轨 it makes an immediate transition from the pass band just immediately to a stop band. This is ideal, but this cannot be implemented. Okay? So therefore, there's a recommendation. Let's truncate. Let's simply keep the middle part. Okay? Let's say, all right, so sooner or later we're gonna disregard everything outside the range from minus n to plus n. We say that, okay, sooner or later we need to just ignore whatever that's outside this range. Truncation, 截断它, truncation. How about just keep the middle part? So by keeping the middle part, we mean we define a filter. Define a filter which now has finitely many samples, okay, many non-zero samples. It has is non-zero only in this region, okay, from minus n to plus n. Truncation, just set it to 0 everywhere else. Otherwise, in the middle, to the left by n and to the right by n, in this interval, in this region, h is exactly equal to g. Okay, it's a fair enough approximation. G goes on. Let's say G goes on, but H now is only defined between plus and minus n. And in that way, we make a truncation. We choose only the middle part. That's the way I put it. 只保留中间, preserve only the middle part, okay? Symmetrically. So let's say we preserve from here to here. And turns out that we can already call this a design. This is already design, a very naive idea. 实际上蛮天真的啊 ，naive, 知道吗 ？Yeah. This idea might look naive. It's French, okay? 天真的啊 ，but actually it's a fair design. It's already a fair design. Seriously. So it means that if we have a filter that is like that, having now 2n plus 1 points, then now can we implement this filter? Yes and no. It's not causal yet, right? But we can shift it all to the right. Now redefine your time zero, right? Now this is the first sample. That one next to it is the second sample. You know what I mean, okay? This is something that can be stored in your computer. And if you allow a delay by n samples, this can be implemented. And it has finitely many samples, a little big, 2n plus 1, maybe 1,000 plus 1, okay? Maybe big, but it can be implemented by storing all the filter coefficients. Okay? Just create a long array and store every coefficient. It can be implemented, hardware or software. Okay? It's already not nice. Kind of this design is not bad. Okay? Naive, but not bad. So now next we should examine the performance in the frequency domain. This is not going to be ideal anymore. Okay? Then what's the resulting frequency response? That's the question we are asking. Right? It's not going to be ideal anymore, but how much does it deviate from ideal? So I may need to draw a bigger picture. I think I do. So let's try to investigate what's the performance, maybe I can just draw here. Yeah. If originally, now going from time to frequency using the Fourier transform, if originally the ideal response is just sharp transition, unity gain, zero passband gain whatsoever, no gain in the passband between minus cutoff frequency and plus cutoff frequency. That's the ideal response. Now we need to find out what will happen in the frequency domain after truncation in time. Okay? So the number one concept we need to notice is that by truncation in time, equivalently, we are multiplying the ideal response with a rectangular window. Okay? We're multiplying this response with a rectangular window. What is that? We'll explain in the next slide. Okay? It's actually multiplication in the time domain. So in the next slide, I argue that truncation can actually be thought of as multiplying the ideal response with a window function. And what's the window function? The window function is all 1 between minus n and n, and 0 elsewhere. And 0 elsewhere. Okay? This is the window function that, so that when you multiply your ideal response with this window function, the resulting design is truncation. Right? Truncation means multiplying by 1 between minus n and plus n, and everywhere else is 0. Right? So just equivalently, truncation means that we are multiplying our ideal response with the window function. Okay? So can we agree on that? That we are multiplying so this is W of n. So W over n is all 1 between minus n and n, including both edges, and 0 elsewhere. 0 elsewhere. That's our window function in the time domain, okay? From minus n to n. That's what's happening when we truncate, when we disregard all the extending samples of the ideal response. Is that clear? So now already we have a multiplication in time. So immediately we know that the frequency response, the Fourier transform of our design denoted by h sub n. N is the length, right? Which is a factor to choose. N is the length. The resulting, so by multiplying in two signals in the time domain, we are doing the corresponding change in the frequency domain is convolution. Okay, so now multiplication time, convolution in the frequency domain. Still, we retain this notation of small letters for time domain, big letters, capital letters for frequency domain. Okay, so now the resulting frequency, the spectrum, the spectrum of this h of the filter as a function of small omega. The spectrum is the convolution between G and omega and W. G and W convolve in the frequency domain. Sorry, this should be theta. Can we all change this to theta? That's wrong. Convolution in the frequency domain, and there's a factor of 1 over 2 pi. And here is a bit, a few remarks about our notations, okay? A few remarks about our notation. First of all, here, instead of ej omega, we simply write omega to emphasize that this is a function of small omega. Okay? You can imagine that this simplifies our notation quite a lot. This simplifies our notations. So that's my first remark. And then the second remark, I also emphasize that now this convolution of frequency domain is denoted by this star sign with a circle around. Some people also call it circular convolution, because actually the angle here is around the circle, a full circle. Okay, circular convolution in the frequency domain, so about which is defined exactly like this. All right, so now here's one more remark I want to make. Please be aware, note that both G and W are real valued in this case. And this will make it easier to plot the frequency response, which we're going to do next. Okay, in the next slide we're going to see exactly what is it we'll visualize what's going on right here. Okay, when we convolve two things in the frequency domain. But first, I want you to notice that both G and W are real valued. Do you know why? Do you know why? Why are they real valued? Because here, first of all, we already know G is real valued. G, the ideal frequency response is real valued. But by definition. But why is big W also real valued? Because similar to G, it is an even symmetric function in time, right? Even symmetry in time, real in the frequency domain. So just both W and G are even functions. Therefore, their Fourier transforms, respectively, 各自的, their Fourier transforms are real values respectively. Both of them are real valued. Okay, so now we are going to finally see in this next slide. In this next slide, we will be looking at the convolution, the circular convolution in the frequency domain. Okay, so now just to point to, as a matter of fact, now here that's what? This is the ideal response, okay, which look rectangular in the frequency domain. Theta is the frequency variable. So let's rewrite. Here, my notation is a bit different. So my notation is h of omega equals to 1 over 2 pi. And there is a, what? G is my ideal response, G theta. And we need to flip and shift W. Flip and shift W. W what? Omega minus theta, d theta. Okay, and we say this is G omega circular convolution with W of omega. Okay. All right. So you have seen that now G is the ideal response, which is ideal. Okay. And the W, this is something that we need to find out. Okay. So it turns out that the Fourier transform of the window is not that hard to calculate. So we can show that there's some ripple-like. This is a periodic sinc function, by the way. Okay, it's a periodic version of the sinc function. That's the Fourier transform of W, which repeats itself every 2 pi. Okay? It's not that hard to make sure that this is indeed the case. It's real value. It can be go positive or negative. Okay? Positive or negatives. So now we want to imagine together. So I invite you to now let's work on this. Can you imagine what's going on when we convolve W and G? This is my G. Okay? When we circularly convolve W and G, what will happen? What will happen? So basically, we're going to take an integral, right? This is about calculating an integral. 做积分嘛, calculate integral. Okay? What is the meaning of an integral? Integral is the area below the curve, right? So basically, we are going to evaluate the area of W now flipped. Okay? We flip W, which turns out to be the same thing because W is also symmetric in the frequency domain. Now, flip W and multiply it with H, flip and shift. Okay, flip W and shift it by omega. So imagine this curve is going to shift to the right and to the left. So we need to repeat this. Okay, so on this plot we have the case of now this is theta. Okay, when we consider convolution, and now this is W of basically theta minus omega. Yeah. And it looks like that. It looks like it's going to have it like that. So we will calculate the area of W times G, with W being flipped, 左右翻过来, and shifted to the right by theta. Then you calculate one area, right? Now you can also shift W to the right and to the left. Let's say now, for the next frequency, we consider W omega is closer to the edge, okay? And then yet another frequency, we consider W now moving outside the passband. W now can move outside further to the right. That's also possible, okay? Or to the left. Now this is doable, like that. Okay. Moving W, I suggest I try to imagine now we're moving W to the right and to the left, because we need to do that for convolution. Okay. And whenever we move it and move it and just let's say just move it and then just evaluate the integral. Move and evaluate the integral. And the result is shown right here. The result now has ripple in the passband as well as ripple in the stop band. That's the result. That's the result that we need to spend a few moments to contemplate. 凝视一下这个感觉啊。When we convolve the Fourier transform of the big W and big G, do we really get this? Do we get this? It makes sense, right? Because when W move outside the passband, W and G do not overlap much, right? Therefore, the area becomes small. But when the main lobe, later we'll learn that this major part is called the main lobe, okay? The main lobe, and we'll come back to this. When the main lobe is within the passband, the area should be large. When the main lobe is moving outside, the area should be small. And the area can also even be negative, depending on where exactly is omega. Okay, so please now when you go home, please convince yourself that indeed when we can visualize convolution like that, okay, by considering the area below a curve. Okay, so I think time is up. So see you tomorrow, and when we have a follow-up discussion. 对，就是这个出现是这两个东西 convolve 的结果。